Hello, everyone, and welcome to Virtual Planetarium from the Museum of Science. My name is Emily. My pronouns are she and her, and I will be your moderator during this program. And we need a moderator because since we're in this webinar format program, if you are watching us on Zoom today, that means that I cannot see or hear any of you. So if you would like to ask questions ask questions of our main educators, you'll need to use the Q&A box in order to do that. So you should be able to see that Q&A button on your screen. Feel free to type in questions throughout the program if you ever have one. We are also offering closed captions during this program, so if you would like to see subtitles, just click on the CC button on your screen and select Show Subtitles. So with that said, I think we can bring on our educators and get started.
Hello, everybody. My name is Talia. I use she, her pronouns, and I am going to be your educator today, but I can't do this alone.
Hi, everyone. My name is Katie. My pronouns are she and her, and today I will be providing your visuals.
So this is the last Tuesday in June, which means it is the end of our galaxy month. We've been talking about galaxies all month long. We've talked about how we've observed them in the past. We've talked about how they form, what kinds they are, and about the giant supermassive black holes that live in their centers. But today we are going to be bringing things a little closer to home. We're going to be focusing specifically on our galaxy, the Milky Way. And when we see the Milky Way in the night sky, this is what it looks like. It looks like this cloudy band going across the sky because we have only ever seen the Milky Way one way, from the inside. It is the only galaxy we can see from the inside. It is also, that means we can't see it from the outside. We're stuck inside of it. So here is a really gorgeous picture with lots of, a time-lapse picture taken from a very dark site, but you do not have to be like in the middle of nowhere necessarily to see the Milky Way. You can see it from pretty much anywhere where there isn't a ton of light pollution. It's not going to be quite so impressive. It's going to look a little bit more like this from a really dark site. And then obviously, the more light pollution there is around you, the fainter it is. It's going to be a little bit harder to see. But this is what it looks like. And you can clearly see there's more going on in that band than there is on either side of it. So people looking up at the sky with their eyes or just basic telescopes, trying to figure out how the Milky Way, what the Milky Way really looked like, figured it must be a disc shape, because everything was concentrated into this band, which goes 360 degrees around the sky. So we know it's in all directions, and it is a very dense band. So that would be the disk that we live inside. And then the above it and below it, that's above and below the disk. So we figured that we lived in a disk. The Milky Way is disc shaped, and we lived in it. And then people actually used to count the stars. William Herschel in particular was famous for actually going out and counting stars to see if he could figure out with a little bit more precision what the shape of the Milky Way might be. And he figured that everything was denser in one direction, the direction of the constellation Sagittarius. So this is where the Milky Way is densest, and there's the stars are generally denser in that patch of sky. That means that's the center. That's the direction of the center. So Sagittarius is a summertime constellation, by the way. If you're ever curious, if you want to go look in the sky in the direction of the center of the Milky Way, just look in the direction of the constellation Sagittarius, and you are in fact looking at the center of the Milky Way. So this is sort of all we could figure out for a long time. We could figure out that probably the Milky Way was disc-shaped. The center of the disk was not where we were. The center of the disk is probably in the direction of Sagittarius. And that was all we could sort of guess with any precision. People really had a very hard time trying to figure out how big the Milky Way is. And that actually does sort of still extend to today. But of course, today, we have modern observatories. We're not just using our eyes or looking at, with very basic telescopes. We've got things like what we're seeing here. That is the Very Large Array, which is a radio observatory. This is the NASA Infrared Telescope Facility, all sorts of things like Hubble. Poor Hubble right now is in a little bit of trouble. Everybody cross your fingers. It's been in safe mode for 2 weeks. They are trying to fix it. Or the Chandra X-ray Observatory, facilities like these, and in the future, things like James Webb or the Nancy Grace Roman Telescope. These allow us to look in far more detail than people could look in the past, and in different kinds of wavelengths, things like the Very Large Array or the Infrared Telescope Facility or the Chandra X-ray Observatory look in types of light that we can't see with our eyes. So using all of these sorts of modern facilities and modern tools at our disposal, we can actually start to build a model of the Milky Way as we think it would look from the outside. And it would look, we think, something like this. Again, humans have never seen the Milky Way from the outside. It would take millions of years for us to get a spacecraft outside the Milky Way to see it from the outside. Clearly that's not going to happen. So we have to figure it out from the inside. We believe that our Milky Way is what we would call a barred spiral galaxy. And what that means is that it has a swirly shape. It's really pretty swirly shape. That's the spiral part. And when we say it is a barred spiral, what we mean is that center area is not actually circular like you see in some spirals. It's sort of stretched out into a football shape. That's the bar. Some spirals have them, some don't. We think the Milky Way does have a spiral or a bar at its center. Now, I said people have been trying to figure out sort of the size of the Milky Way for a very long time. They actually still are. We're not completely sure how big the Milky Way is. It's somewhere between 100,000 and 150,000 light years across. So what that means is that if you are on the very edge of the galaxy and you sent a radio signal out, it would take somewhere between 100,000 and 150,000 years for that signal to cross all the way to the other side of the galaxy. So that sounds pretty big, right? How do you think that compares in terms of other galaxies? Where do you think the Milky Way ranks in terms of galaxy size? Is it some of the biggest, some of the smallest, right in the middle? What do you think? Go ahead and put your answer in the Q&A. You can put question marks if you don't want to take a guess, but go ahead and make a guess. At 100,000 to 150,000 light years across, where do you think the Milky Way ranks in terms of galaxy size?
So I'm just going to give everyone a few moments to put in their guesses. Let's see, I'm getting 2 people thinking, actually 3 now, saying that it's small. And then a couple people also saying maybe an average sort of middle-sized galaxy.
And that's about right. It's sort of on the bigger side of average. Mostly because there is actually a lot of galaxies out there that are very small that we call dwarf galaxies. There may only be 1,000 light years across or less. There are galaxies out there that make the Milky Way look small though. There's the largest galaxy we've ever found was something like 5 million light years across. So that is ridiculously bigger than the Milky Way. But the Milky Way is actually a pretty good sized galaxy at about 100 to 150,000 light years across. Now that's of course when you're looking at it this way. We said several times the Milky Way is a disk. That means if you look at it from a different angle, it looks a lot skinnier, a lot skinnier. The Milky Way is flat. It's sort of like a dinner plate. And that's true of all spirals. Spirals are very wide in one direction and very, very thin in when you look at them from the edge. They can almost disappear when you look at them from the edge. In thickness, it's anywhere from 1,000 to 3,000 light years thick. So we live out in the disk. It's about 1,000 light years thick out there. The very center, the bulge, which is another distinct feature of spirals, is about 3,000 light years thick. So about 1,000 to 3,000 light years thick, 100,000 to 150,000 light years across, and it's spinning. This whole galaxy is rotating, spinning like a pinwheel. And I'm kind of curious, if you wanted to, let's make another guess. how long do you think it takes the Milky Way to rotate once, to complete one full spin? Go ahead and put your best guesses in the Q&A.
That's a really fun question. I predict we'll get a lot of different answers, but again, we'll give folks a few moments to put in their guesses. How long does it take the Milky Way to spin?
One complete rotation.
Yeah, someone is thinking maybe 1 million years, maybe 1,000 years. Those are the only two I've seen so far. Maybe 25 million years.
So definitely not something that's happening like once a year or anything. We've definitely got that sense. Well, it turns out that something this big spins pretty slowly, or at least it takes a long time to complete a rotation. The Milky Way rotates once every 250 million years, which means the last time the sun was at this rotation point in the galaxy, the dinosaurs weren't really there yet. They kind of hadn't gotten their start yet. And that actually means that most of the dinosaurs lived completely on the opposite side of the galaxy, because it was about half a rotation ago that dinosaurs were really at their peak. So it takes a very long time for the Milky Way to complete a full rotation. Now our sun, which Katie has marked for us, you can see that crosshair there, that marks the location of the sun. We are in the middle of the disk. Sort of out in the suburbs, if you will, not in the center where it's very, very crowded, not at the edge where where it's very, very diffuse. We are about half to 2/3 of the way out of the disk, about 26,000 light years from the center. That's good. I mean, that means we're 26,000 light years from the supermassive black hole in the middle, which is a good thing. And in terms of the population of the Milky Way, the sun is one of several 100 billion stars in the Milky Way. You notice I'm throwing out a ton of big numbers, hundreds of thousands, hundreds of millions, and now we're into hundreds of billions in terms of the number of stars in the Milky Way. Once you start talking about galaxies, numbers get very big, very fast. There's somewhere between 200 and 400 billion stars in the Milky Way. And probably according to what we've learned from the Kepler telescope, we think there are probably about the same number of planets out there as there are stars. Now, I'm going to go ahead and ask, instead of a guess, I would like you guys to go ahead and write into the Q&A any observations you're making about the Milky Way here. Just anything you notice. Really anything. Go ahead and write those in the Q&A. Share them with Emily. It can be color, it can be shape, it can be size, it can be distribution, it can be density.
So I just want to share that one person is going crazy over the number of stars that are in the Milky Way. They're very impressed. But someone is saying they're noticing that the Milky Way is much brighter in the center of the galaxy. Someone else is noticing the spiral arms that are emanating from the center.
Absolutely, these are great observations.
Someone says, I think that the swirls are stars. So again, maybe those arms are just packed full of stars. Someone else thinks that it's not very colorful, maybe not as colorful as they thought it would be.
These are all great. All right, let's talk about some of these. So yeah, somebody noticed that a lot of in fact, these were all fantastic observations. The colors, the different brightness in the center versus the arms, just the existence of the arms, and what is going on in the arms. Those are all fantastic observations. So let's start with the differences in color. Because if you notice, there's not a lot of color variation, but the center is very, very yellow, very sort of reddish yellow. And the arms have other colors in them. They've got the bright pinks. There's sort of these bluish colors happening as well. And that's because things are very different in the arms than they are in the center. In the arms, you have star formation happening. Those arms are density waves that are just packing, those are where stars and gas clouds are very tightly, are more tightly packed together than in between the arms. And when you pack gas clouds together, that's how it's good. You get good conditions for star formation. So anywhere where you see those bright sort of pinkish patches along the arms, those are places where a lot of star formation is happening. Active star formation. And where you see the bluish color in some places in the arms, the bluish white colors, that's because where you have a lot of star formation, you have a lot of very young, very hot stars. Young, hot stars burn bluish white. Think about our sun for a second. Our sun is kind of middle of the road in terms of age and temperature. It burns kind of yellow. The young, really, really hot stars, they burn bright blue. So you're going to get a lot of those happening in the arms because there's a lot of star formation happening in the arms. There's a lot of gas. The density waves of the arms are causing that gas to push together in places. Lots of star formation is happening in the arms. Then you go to the center. The center doesn't have that bluish color. The center is very reddish yellow. There's not a lot of gas in the middle of the galaxy. Without gas, you can't make new stars. So those bright blue stars, those really, really hot ones, they actually don't live very long. So in order for there to be a bluish color, you need to keep making more, but you can't keep making more in the middle. There's just not the gas for it. So the young hot stars died off a long time ago and left the more temperate stars, the ones that burn slower but burn at not quite as high a temperature. And those stars tend to be reddish, yellowish stars. And there's a lot of them in the center of the galaxy. So that is why and they're very, very tightly packed. So that's why the middle of the galaxy is a different color than the arms. And the brightness, somebody picked up on the brightness difference between the middle of the galaxy and the arms. That's because things are so much more tightly packed together in the center than they are in the arms. Out where we are, right? We're out in the arms. We're on one of the, we think, we're not sure actually yet. It keeps changing whether we're on a minor arm or a major arm. But out where we are, there's 4 light years between us and the next star. Our next door neighbor star, 4 light years. So out where we are, there's a couple of light years in between star systems. In the center of the galaxy, the stars are very tightly packed. There are millions of stars packed within just a few thousand light years. So those stars are very closely packed together. If you were on a planet, on a star in the middle, it would be really, really bright. You wouldn't get a good nighttime, and you'd be constantly getting blasted by radiation from all those stars. Probably you wouldn't be alive. So it's a good thing we don't live on a planet in the middle of the galaxy. And then, of course, at the very center of that bulge in the middle, that's where the supermassive black hole lives, at the very center of the galaxy. And if you were here for Katie's presentation last week, you know that actually these black holes play a huge role in keeping the galaxy together. They play a huge structural role. The gravity of that black hole is really holding the center of the galaxy together, and that helps hold the outer part of the galaxy together. So that's a lot about the structure of the Milky Way. What about, where did it come from? Where's it going? So the Milky Way, we think, is not one of the oldest galaxies in the universe. We think it's somewhere around 10 billion years old. Again, we're working with really big numbers. So that makes it old, but it's not super old. Now it contains some stars inside of it are older. It contains some very, very old stars. Now that can be either because probably the small progenitor galaxies that combined together to originally form the Milky Way had very old stars in them, or the Milky Way may have eaten a very small old galaxy and taken all its stars in and made it part of itself. So although the galaxy is about 10 billion years old, there are stars in the Milky Way that are more like 13 billion years old, which is very, very old. So we think it probably grew up to its current size through collisions with, like I said, smaller galaxies coming together and merging to form a bigger galaxy. That's probably where the Milky Way got its start. And it has continued to grow by pulling in smaller galaxies and making them a part of itself. It is still doing that. And of course, there is the big collision that is coming. In about 4.5 billion years, give or take, the Milky Way is going to collide with our nearest large neighbor galaxy, which is the Andromeda Galaxy. So here's a model of that collision. And you can see in the corner the number of years from now into the future that this will be. Right now, Andromeda is about 2.5 million light years away from us, which sounds very far, and it is. But it is getting closer. The gravity of these two large galaxies is drawing them towards each other. And so somewhere around 4 to 4.5 billion years from now, they're going to get very close. They're going to swirl around each other a bit. And then they're ultimately going to combine and form what they're currently calling the Milky Galaxy. I feel like we should come up with a different name for it. We've got about 4.5 billion years to come up with a better name than Milky. Now, as I said, this main collision is going to start in something like 4.5 billion years. But in some sense, it's already started, because these two galaxies both have big, huge halos of dark matter, and those halos are probably already colliding. So when we were really first trying to get to know the Milky Way with modern telescopes, we observed the rotation, how fast the Milky Way is rotating. And we figured that the Milky Way actually ought to be rotating faster near the center than it is at the edges. Just like Mercury, because it's closer to the sun, moves faster around the sun than, say, Jupiter does. So the area of the galaxy towards the middle should be rotating faster than the stuff on the outside. It's not, though. It's all rotating at roughly the same pace. It all takes about 250 million years to rotate. And the answer to that riddle is that there's a lot more mass than what we can see. In fact, what we can see, that beautiful model of the Milky Way we've been showing you this whole time, that must be only about 10% of the matter that is in the Milky Way. And all the rest of it must be something we can't see. This is actually how we discovered that dark matter existed in the first place. So what you're seeing here is a model of the Milky Way with an artist's rendition of sort of what the dark matter halo would look like. Of course, we can't see the dark matter halo. It's in all directions around the Milky Way. And we can't see it, but we know it's got to be there because of the gravitational effects. So we estimate that our dark matter halo, this cloud of dark matter around the Milky Way, extends something like 2 million light years out from the disk that we can see. 2 million light years. I told you that Andromeda is 2.5 million light years away. And Andromeda has to have a halo of its own. So those halos are probably already colliding. So in one sense, we are already colliding with Andromeda. Now, I'm sure you're wondering, well, wait, why can't you tell us a little bit more about what dark matter is? It's because A, I really can't. B, if you do want to know more about dark matter, tune in next week, because Katie's going to be telling us a little bit about dark matter and what it is and how it works, or what we think it is and how we think it might work. But in the meantime, let's go back to a picture of our Milky Way, the way we think it looks out in space. And I'm happy to open it up for any questions that might have come in along the way.
Thank you, Talia. That was awesome. I only have one question that I've seen in the chat so far. And someone was wondering how big the Andromeda Galaxy is from one end to the other. And why don't you also tell us how many stars are in it compared to the Milky Way?
So the Andromeda is bigger than the Milky Way. And it is about 5 times the size of the Milky Way. So it's probably close to 500,000 light years across and contains somewhere around 1 trillion stars. Again, those are estimates, give or take 100 billion. But it is bigger than the Milky Way. And we used to think it was about twice the size of the Milky Way. Now we think it's about 5 times the size of the Milky Way.
Awesome.
Pretty large.
So I am stalling a little bit just to see if more questions come in. But honestly, I think you've just left everyone in awe. They're all mesmerized by what you've been talking about.
Like I said, I threw out a lot of really big numbers. Once you start getting into the specifics about galaxies, the numbers get very, very big, very, very quickly.
Let's do, how about one more question, because we are almost out of time. Is the sun small compared to other stars in our galaxy?
That is an excellent question. And the answer is yes and no also. We like to say the sun is sort of a middle of the road star, like a medium-sized star. And Katie's bringing us in so we can get a good look at it. And what we mean by that isn't that, you know, there's like the sun's sort of average. What we mean is that there are stars out there that are way bigger than the sun, and there are also stars that are way smaller than the sun. The biggest stars that we see in our Milky Way, if you put them in the sun's place, they would extend out past the orbit of Saturn. So if you sort of think of what our solar system looks like, they would extend out past the orbit of Saturn. That is a very, very, very huge star. But there are also stars out there that are, and here's the sort of demonstration. Saturn is that second yellow one. So imagine putting something in the sun's place that extends out past that second yellow line. That is the orbit of Saturn. But there are also stars that we found that are really only about the size of like Jupiter or Saturn, which is big compared to the Earth, but not compared to the sun. You could fit, you know, something like 10,000 Jupiters inside the sun, but we have found stars that are about as small as Jupiter in terms of size. So there's actually a huge range of star sizes out there. Sun is kind of in the middle in terms of the size. I will say the small ones are way more common than the big ones. You're going to see a lot of those tinier, redder stars than the really big blue ones.
All right. Awesome. Thank you so much, Talia. I do recommend checking out the Q&A box before you sign off, because a lot of people are saying how much they enjoyed this program. So thank you. Katie and Talia, do you want to say goodbye to everyone?
Bye, everyone.
Bye, everyone.
All right. And folks, we are officially out of time. Thank you so much for joining us today. We always have fun talking to you and hearing what kind of questions you have about space. If you want to check out more of our virtual offerings, you can go to mos.org/mos@home. And then if you would like to support the museum, you can visit engage.mos.org/welcome. So with that, we will see you next Tuesday talking about dark matter, according to Talia. And we hope you have a great day and a great week. Bye.